All right, let's go.
Number 12. Einstein's postulate, the single sentence that broke classical physics. In 1905, Albert Einstein published a paper containing a claim so strange that physicists spent the following decades working out its full implications. The speed of light in a vacuum, roughly 299,792 kilometers per second, is exactly the same for every observer, regardless of how fast that observer is moving, and regardless of how fast the source of the light is moving. In ordinary experience, speeds add together. A ball thrown forward from a moving train appears faster to someone standing outside the train than to someone inside the train. Light refuses to follow that rule. A beam of light measured by someone standing still and a beam of light measured by someone chasing after it at 99% the speed of light will both be measured by each observer as traveling at exactly 299,792 kilometers per second. This single rigid fact is called the invariance of the speed of light, and it is the postulate on which Einstein built special relativity. Every strange conclusion that follows about time, distance, and the nature of light itself flows directly out of this one starting assumption, verified experimentally many thousands of times over the following century and never once found to be violated.
Number 11. Proper time along a light path is exactly zero. The mathematics that physicists take completely seriously. Special and general relativity both define a quantity called proper time, essentially the time an object actually experiences as measured by a clock traveling along with it. For any object moving slower than light, proper time increases steadily as the object moves through space, though it increases more slowly the faster the object travels, an effect called time dilation. For a photon, a particle of light, physicists calculate this quantity and get exactly zero for any journey of any length whatsoever. The trajectory light follows through space-time is called a null geodesic, named specifically because the proper time interval along it vanishes completely. This is not an approximation or a rounding error. It is an exact mathematical result derived directly from the structure of relativity, discussed as far back as physicist Wolfgang Rindler's foundational relativity textbooks and reaffirmed in essentially every serious treatment of the subject since. A photon emitted from the surface of the sun and absorbed by your eye 8 minutes later by any clock traveling along with that photon takes exactly zero time to make the trip. Not a very short time, zero. The photon's clock, if such a clock could exist, never ticks at all, regardless of the distance the photon actually crosses.
Number 10. Light has no valid reference frame of its own, a direct contradiction baked into the theory's own rules. Given that proper time is zero for photons, an obvious question follows. What does the universe look like from a photon's own point of view? The honest answer, agreed upon by essentially the entire physics community, is that the question itself is not valid, and asking it produces contradictions rather than answers. Special relativity is built on reference frames, coordinate systems attached to specific observers that let physicists describe motion, time, and distance consistently. Every valid reference frame in special relativity is required to move at a speed strictly slower than light. If you tried to construct a reference frame in which a photon is at rest, you would need that photon to have a speed of zero within its own frame. But Einstein's foundational postulate specifically requires the speed of light to equal exactly 299,792 kilometers per second in every legitimate frame of reference, with no exceptions. A frame in which light is stationary would need light speed to simultaneously equal zero and equal 299,792 kilometers per second, a direct contradiction. Physicists resolve this not by finding an answer, but by concluding no such frame can exist within the theory at all. Light does not experience the universe from any coherent perspective, not because nobody has figured out the math yet, but because relativity's own internal logic forbids the perspective from being constructed in the first place.
Number 9. Length contracts to zero along the direction of light's motion, the other half of the same impossible equation. Time dilation has a companion effect called length contraction. As an object's speed increases, the distance it appears to travel, measured along its direction of motion, shrinks from the perspective of an observer watching it move. The faster the object goes, the more severe the contraction becomes. Run the length contraction formula for an object moving at the speed of light, and the result again lands on exactly 0. Any distance whatsoever, from the width of a single atom to the full diameter of the observable universe, would contract down to 0 length for something genuinely traveling at speed light. Physicists sometimes describe this by saying that from a hypothetical photon perspective, the 8 light-minute journey from the Sun to Earth involves no distance to cross at all. This pairs precisely with the 0 proper time from the previous entry. There is no time for the journey to take and no distance for the journey to cover. The two zeros cancel out consistently within the mathematics, but the physical picture they paint, an entire universe collapsed into a single point with no elapsed duration, is one that has no coherent everyday translation. It is not that light experiences the universe strangely, it is that by the theory's own terms, light does not experience anything that can be called a journey at all.
Number 8. The Shapiro Delay. Light genuinely, measurably slows near mass. Real experimental proof that the speed of light is not as fixed as it sounds. In 1964, physicist Erwin Shapiro proposed a fourth classical test of general relativity, beyond the 3 tests Einstein himself had already suggested. Shapiro predicted that radar signals bounced off a planet on the far side of the Sun, passing close by the Sun's gravity on their way there and back, should arrive measurably later than a simple distance calculation would predict, because the Sun's gravitational field curves the surrounding spacetime and effectively slows the coordinate speed of the light passing through it. Shapiro tested this directly by bouncing radar signals off Venus and Mercury as they passed near solar conjunction, and the delay he measured, close to 200 microseconds, matched his general relativistic prediction with remarkable precision. The experiment has since been repeated with far greater accuracy, most notably in 2003 using the Cassini spacecraft, confirming Einstein's prediction to within roughly 1 part in 100,000. The nuance that makes this result genuinely disturbing rather than merely a curiosity. Locally, at any single point along its path, light always still measures at exactly 299,792 kilometers per second, satisfying Einstein's postulate. But the coordinate speed, the speed calculated by a distant observer watching light travel through curved spacetime near a massive object, is measurably, provably lower than it would be in flat, empty space. Gravity does not just bend light's path, it genuinely delays it in a way distant observers can time with a stopwatch. Number 7. Light freezes completely at a black hole's event horizon. For an outside observer, the speed of light effectively reaches 0. Push the Shapiro delay effect to its most extreme conceivable limit, and something remarkable happens at the boundary of a black hole. As light climbs outward from deeper and deeper inside a black hole's gravitational well, general relativity predicts it takes longer and longer, from a distant observer's perspective, to make any further progress outward. Exactly at the event horizon, the mathematics gives a genuinely infinite delay. This produces one of general relativity's strangest confirmed predictions, sometimes called the frozen star effect. An object falling toward a black hole appears, to any observer safely outside the event horizon, to move slower and slower as it approaches the horizon, its light growing dimmer and increasingly redshifted, without that observer ever actually witnessing it cross the boundary. Physicist Robert Penna's 2012 paper on collapsing shells directly confirmed this mathematically, showing that a distant observer never sees any part of infalling matter cross the horizon. The image simply freezes there, asymptotically, forever fading toward invisibility rather than vanishing at a specific instant. From the perspective of anyone actually falling in, none of this applies. They cross the horizon in an entirely ordinary, finite amount of their own proper time, and notice nothing unusual at the boundary itself.
But for every observer who stays outside, light emitted at the horizon takes an infinite coordinate time to escape, and the effective speed of that escaping light, from the outside perspective, asymptotically approaches zero and never quite gets there. It is the closest general relativity comes to describing light's velocity as genuinely reaching zero anywhere in the universe.
Number 6. Variable speed of light cosmology. Serious physicists proposing that C itself has changed over cosmic history. Robert Dicke first raised the possibility that the speed of light might not be a truly fixed constant as early as the 1930s, but the idea gained serious traction in the 1990s through two independent lines of research. Physicist John Moffat proposed in 1992 that the speed of light was dramatically higher in the extremely early universe, potentially by a factor of trillions upon trillions, before dropping through some kind of phase transition to the much lower value we measure today. A few years later, physicist Andreas Albrecht and Jaume Guijo independently developed a related variable speed of light model published in Physical Review D in 1999, exploring the same core idea from a different theoretical angle. Both proposals were motivated by a genuine long-standing puzzle in cosmology called the horizon puzzle. Distant regions of the observable universe display nearly identical temperatures and properties, despite appearing under a constant speed of light to have never been close enough to exchange any information or reach thermal equilibrium with each other. The dominant mainstream solution to this puzzle is cosmic inflation, an extremely rapid expansion of space in the universe's first fraction of a second. Variable speed of light cosmology proposes an entirely different resolution. If light itself traveled far faster in the extremely early universe, distant regions could have been in causal contact after all, without requiring inflation at all. These models remain speculative and are not part of mainstream cosmology, since they require abandoning strict Lorentz invariance, the same symmetry principle underlying Einstein's original 1905 postulate. But they have been published, debated, and refined in peer-reviewed physics literature for over 3 decades, precisely because the horizon puzzle they attempt to solve is a genuine unresolved feature of standard cosmology. Number 5. Doubly special relativity, making the speed of light itself depend on a particle's energy. A related and even stranger proposal developed primarily by João Magalhães working with theoretical physicist Lee Smolin in the early 2000s suggests that the speed of light might not be constant even at a fixed moment in cosmic history, but could instead depend on the energy of the specific photon in question. Under this framework called doubly special relativity, extremely high-energy photons, those approaching the Planck energy scale, in almost unimaginably extreme energy, far beyond anything produced in any particle accelerator on Earth, would travel measurably slower than the low-energy photons that make up ordinary visible light. The theoretical motivation is an attempt to reconcile general relativity with quantum mechanics at the smallest possible scales, the realm of quantum gravity, by introducing a second invariant quantity, the Planck length, alongside the speed of light itself, which is why the framework is called doubly special. One proposed way to test the idea observationally involves gamma-ray bursts, extraordinarily energetic cosmic explosions that emit photons across an enormous range of energies simultaneously from a single extremely distant source. If Magalhães and Smolin's proposal is correct, the highest energy photons from a given gamma-ray burst should arrive measurably later than the lowest energy photons, having traveled billions of light-years at an infinitesimally slower effective speed. Multiple gamma-ray burst observations, including data gathered by the Fermi Gamma-Ray Space Telescope, have searched for exactly this signature and have so far found no confirmed energy-dependent delay beyond what ordinary astrophysical explanations can account for, placing increasingly tight constraints on how large any such effect could possibly be, without yet ruling the entire idea out completely. Number 4. The fine structure constant dipole. Evidence that the rules of light itself might differ across the sky. The fine structure constant, a dimensionless number close to 1 divided by 137, governs the strength of the electromagnetic interaction and is mathematically tied directly to the speed of light.
Beginning in 1999, physicist John Webb at the University of New South Wales and his collaborators began publishing results based on analyzing the light absorbed by ancient mass clouds in front of extremely distant quasars, suggesting that this supposedly fixed constant might have had a slightly different value billions of years ago than it does today. The most striking version of this claim came in 2010 and 2011, when Webb's team combined data from the Keck telescope in Hawaii, which looks primarily toward the northern sky, with new data from the Very Large Telescope in Chile, which looks primarily toward the south. The two datasets showed opposite trends. The fine structure constant appeared to have been very slightly smaller in the ancient past when measured in one direction of the sky, and very slightly larger in the ancient past when measured in the opposite direction, a pattern the team described as a dipole, published with a statistical significance about 4 standard deviations. If confirmed, this would mean the fundamental rules governing light and electromagnetism are not the same in every direction of the universe. The claim has faced serious, ongoing scientific scrutiny. Physicists Cameron and Pettit published detailed criticisms in 2012, highlighting possible unaccounted systematic errors tied to the alignment between the dipole's axis and the telescope's own viewing directions. Most recently, a 2024 analysis using James Webb Space Telescope observations of extremely distant galaxies found no evidence for any cosmic evolution of the fine structure constant at all, adding further tension to Webb's original dipole result. As of the most recent research, the question remains genuinely unresolved, sitting exactly at the boundary between an exciting real discovery and an unexplained systematic error nobody has yet fully identified. Number 3. Why mainstream physics remains deeply skeptical. The overwhelming weight of evidence still favors a truly constant c. Every proposal on this list challenging the constancy of light speed, from variable speed of light cosmology to doubly special relativity to the fine structure constant dipole, runs directly against an enormous body of extremely precise experimental evidence supporting Lorentz invariance, the principle that the laws of physics, including a fixed speed of light, look the same for every observer in uniform motion. Modern tests of Lorentz invariance using techniques including comparisons between different types of atomic clocks, precision laser interferometry, and analysis of astrophysical particle showers have constrained any possible violation to levels many orders of magnitude smaller than what would be needed to produce most of the effects these speculative theories propose. Physicist John Moffat's own early variable speed of light proposal required Lorentz invariance to be broken outright, a step the vast majority of physicists remain unwilling to take without significantly more compelling direct evidence. This is precisely why entries 6 through 4 on this list are described honestly as disturbing rather than as established fact. They are not fringe nonsense. They are published, peer-reviewed physics, taken seriously enough to generate ongoing experimental searches, decades of refinement, and genuine scientific debate. But they remain minority positions specifically because the mainstream alternative, in which the speed of light truly is fixed everywhere, at every energy, in every direction, continues to match essentially every precision experiment performed to test it. Number 2. What zero actually means across all of this. Two very different kinds of zero, both genuinely part of physics. Line up everything covered so far, and there are really two separate, unrelated ways the number 0 enters discussions of the speed of light, and conflating them is where most confusion about this topic comes from. The first is the 0 baked into relativity's own foundational mathematics. Proper time along any light path is exactly 0. Length contraction along light's direction of motion is exactly 0. And no valid reference frame exists in which light's own speed could be measured as 0 without contradicting Einstein's postulate. This is not a claim that light's speed changes. It is closer to a statement that the concept of speed, duration, and distance simply stop applying meaningfully to something moving at exactly light speed, producing a mathematical form of 0 at both ends of a journey that from every other reference frame in the universe clearly takes real time and covers real distance. The second is an entirely different physical kind of near zero. The Shapiro delay's genuine, measured slowing of light's coordinate speed near mass, pushed to its logical extreme at a black hole's event horizon, where the effective speed of escaping light, as calculated by any distant observer, asymptotically approaches zero without a hard mathematical singularity forcing it there instantly. This is a real, externally measurable effect confirmed by spacecraft radar experiments, not a reference frame paradox. And separately again, sitting outside both of those categories entirely is a small set of genuinely speculative but professionally published theories proposing that the number 299,792 kilometers per second, the value we currently measure, might not be a truly fixed constant of nature at all across cosmic history, across the electromagnetic spectrum's full energy range, or across different directions of the observable sky. Number 1, what this actually reveals about light. None of this means the speed of light is secretly zero in any everyday sense. Every measurement performed on Earth, in the solar system, and across the observable universe continues to return the same value, 299,792 kilometers per second, to extraordinary precision. GPS satellites work, radio communications with spacecraft billions of kilometers away work. None of that changes. What the honest, disturbing version of this topic actually reveals is that the number itself sits at the exact center of several genuinely unresolved tensions in physics. Relativity's own internal mathematics forces light's proper time and length from any hypothetical perspective riding along with it to zero, while simultaneously forbidding that perspective from ever being constructed as a valid frame of reference at all. A contradiction relativity resolves only by declaring the question itself out of bounds. Confirmed general relativistic effects genuinely slow light's coordinate speed near mass, all the way down to an asymptotic, never quite reached zero at a black hole's horizon. And a small, persistent, professionally published thread of cosmology continues to ask whether the value we measure today has always held true, across every era, every energy, and every direction of the sky. A question current evidence leans firmly against, but has not yet definitively closed. Light is the one thing in the universe every other measurement is built around, the fixed ruler used to define distance, time, and causality itself. And even that ruler, looked at closely enough, from close enough to a black hole, or far back enough into cosmic history, turns out to have far more genuine uncertainty folded into it than the tidy, unchanging number printed in every physics textbook. Subscribe to Cosmic Hives. See you in the next one.